All right, let's get started. Okay, so my name is Simon. I am the stupid astronomer because I do the stupid thing so you don't have to. And we are here with Teledyne Systems, Mike, who is going to be doing this amazing talk about dynamic range and why your camera is a liar. So I'm actually quite intrigued by this one because I know why my camera lies because, it's my camera. The question is I'm going to find out why it's lying to me. So Mike, tell us a little bit about yourself first before we get started.
Yeah, so just so everyone knows, I've been doing optics and imaging for 20 years. I have a PhD in cell molecular biology, and I kind of got started in life as a microscopist and branched out into other things, including more than a fair bit of astronomy. I work for Teledyne. I kind of represent us in the Southwest, which includes, a few observatories in the country. And I'll be talking today. This is kind of the second in a series. So I don't know. I think a lot of you were here for the first talk, but we'll do a bit of a refresher because this kind of builds on it. And we'll talk about the concept of dynamic range. You might be asking, like, who is Teledyne and why do you guys know anything about this? So I'll just mention in case people don't know who we are. Teledyne is a company that basically builds electromagnetic sensors and scientific imaging apparatus of all different kinds. We bill ourselves as fairly unique in the sense that we control the fab, we make and fabricate the sensors themselves, whether it's CMOS or CCD, all in all kinds of different materials. Everyone thinks of CCD and sensors as silicon, but a lot of things, like I'll show a slide on the JWST in a minute, those are all mercury cadmium telluride sensors. Having the ability to control what materials we use to make the sensors all the way up through making our own cameras out of those, primarily geared for people doing, science, astronomy, things at kind of the higher end. We tend not to do consumer level stuff. We've done a fair amount of projects for space and for astronomy and for imaging. This is just kind of a little overview of some of the things we've done. Everyone knows of the Perseverance. Most of the instrumentation on the Perseverance is Teledyne. And the same is true of the JWST. We like to say 99% of the pixels on the JWST were provided by Teledyne. And this slide has a little bit of this here. I'm not going to belabor the point too much. We'll kind of move on to the topic that we're here to talk about today, which is really dynamic range. Probably the single most boring topic one can talk about when it comes to cameras. But I'm going to try to make it a little more exciting and try to tell you a little bit about why it's important. It's an aspect, everyone looks at quantum efficiency, at noise levels, and dynamic range tends to get overlooked when you're looking at those other things. But they're all interrelated. And so we'll talk a little bit about what exactly dynamic range is, because it's not quite as simple as you might think. And I'll give you the tools on how you can calculate it yourself for any camera that you're looking at, whether it's ours or someone else's, and it'll allow you to figure out if your camera is lying to you. And we'll talk about what I mean by that. And we'll do a little bit of a hit on something called extended dynamic range, which is really a newer topic. It's really more to do with things that are going on at the CMOS level. So just a bit of a reminder from the last talk, we outlined the structure of a pixel. And in this case, trying to be as generic as possible. There's a lot of different kinds of sensors. CMOS sensors are rising up. But no matter what kind of sensor you have, if it's a device that's converting photons into electrons, it's going to have a structure very similar to what I'm showing you here. The thing we're most concerned about are these individual pixels and what's going on in one pixel. Because if we can understand what happens in one pixel, we can understand what happens in 1 million, 10 million, 64 million pixels, right? Kind of all at the same time. And the business end is this depleted region, which is the area that actually stores the photoelectrons before it gets read out as an image that you ultimately see. So when it comes to dynamic range, I wanted to start by just talking about what it is and kind of why it matters. And oh, by the way, as we're going along here, I put something in the chat, but if you have questions that you'd like to have me address afterwards, or have Simon tap me on the shoulder, virtually speaking, feel free to put those in the chat. And of course, we'll do a Q&A afterwards as well. So humans, according to the latest data, can see 450 shades of gray. And this is nothing to do with, you know, rather risque movies of the same sorts of titles. This has to do with how well you can distinguish light from dark and gradations thereof. For humans, we kind of take it for granted that we can see these shades of gray and light and dark and in between. But for a lot of scientific experiments, and especially for spectroscopy, which is a bigger and growing area in astronomy, it's really critical to be able to distinguish fairly subtle differences on the order of tenths or hundredths of a percent in some cases. So if we look at this kind of standard Kodak bar here, you'll see 20 gray values is on the top. And what you'll see is if you wanted to tell the difference between number 4 and number 5, and the gray value somewhere in between there, right? If you're only on a 20-bit scale, you can't tell, or 20 gray value scale, you can't tell. If we go to, this is 8-bit, below that, 256 gray values, kind of old school computer, then you can more easily distinguish between, say, this 4 and 5 gray value. You can come up with a 4.2 or 4.3, this kind of thing. And so you can start to make finer measurements. So how does this translate to your camera? Well, every camera has a full well capacity. This is the amount of data or number of electrons that can be stored in one well on the camera, or one pixel. And this can vary widely depending on what the camera is. Dynamic range is a function of this full well capacity. So we need to know what the full well capacity is to understand dynamic range. In this example here, I'm looking at a camera that has a 12.8 micron by 12.8 micron pixel. It happens to have a full well capacity of 130,000 electrons. It's not quite as simple as being a function of the chip that's used, but the chip that's used impacts this more than anything else. There's some tuning you can do as the cameras are built and kind of in how you run it, but the chip kind of sets the baseline from where you can kind of make it bigger or smaller. And here's just a few examples using some of our cameras. This one on the left is a CMOS camera that we make. It uses a 6.5 micron pixel. You'll notice with the smaller pixel, the full well is smaller, 15,000 electrons, right? Not a surprise. It's not exactly linear, and I'll tell you why on that in a second, but it's really a function of pixel size. And so a larger pixel size camera like this Sophia shown here is going to have 10 times the full well capacity of the CMOS camera. Now you might think that means 10 times the dynamic range. Again, not quite that simple. We'll get there in a second, so bear with me. If you look at another camera we make, the Pixis, 100,000 electron full well. So you'll notice that the full well capacity is a function of the chip, the camera, and the pixel size. But one unappreciated little factoid I'll give you with today, a lot of astronomers like to use a type of chip called deep depletion. These deep depletion chips are more sensitive in the near IR, and they also have another fortuitous side effect. They're more sensitive in the near IR because the pixel area is thicker. It's harder for a photon to go through it without getting caught. And so weakly energetic photons in the near IR are much more easily captured with one of these types of chips. Because the area is thicker that the photon has to go through, the volume of the well goes up, the full well capacity goes up. I show you an example here where the exact same sensor in a deep depletion and in a standard back illuminated version, you have 2.5 times the full well capacity in the deep depletion version. So this is another reason astronomers like deep depletion chips. It also gives you a higher dynamic range, a better ability to see those really fine distinctions between things. And for pretty pictures, to be able to really capture the full range of a picture, especially for brighter objects, if you're doing things like lunar photography or you're doing things like solar work where you've got an infinite amount of light, it's nice to be able to capture all that. Excuse me. So how does this, so I've talked a lot now about full well capacity, and you might say, well, I thought we were talking about dynamic range. We are. The reason is that one is kind of a function of the other. Dynamic range is actually the full well capacity on your camera divided by the smallest unit of measure, which is the read noise. This makes sense if you think about it. You want to measure how much is in this well in order to figure out how many gradations you see. you can't see a gradation smaller than the noise associated with the measurement. So if you think about it that way, it's really pretty simple math. I'm actually a PhD biologist who got into optics, so I'm not, I'm not a super mathematician, but I can do basic algebra. And so if we look at this Sophia 2K that I used in the previous example with 108,000 electron full well, you divide this by 3.3 electrons, which is the read noise. These are generally published specs for a camera. I'm not going to talk about whether those published specs are right. For us, we measure them and base them on actual production cameras. But let's assume for sake of this discussion that your specs are right on. In this case, this camera can see 32,737 shades of gray. A lot of CCDs have a trick they can do where you can bend the chip to increase the dynamic range. You can do that with this camera. If you do it, you wind up with a higher full well capacity, and you wind up with 76,121 shades of gray. So this camera, when we build it, is actually 18 bits because, and we'll talk more about that in a second, but ideally the output of the camera is matched to this dynamic range number. So here's how to know if your camera is lying. And that's what cameras are often lying about, sort of lying by implication as to how they're actually outputting the data. Ideally, the scale of the output of the camera should match the dynamic range. If the camera puts out a scale of 0 to 65,000 gray levels or ADUs, ideally, the camera can see 65,000 shades of gray. But in reality, there is actually no relationship between the analog to digital converter, which produces this number you see on the computer screen, and the camera's true dynamic range. They should be related, but they're not necessarily. You can take a camera with a very low dynamic range, put a 16-bit A to D converter on it, and you're going to get a number that's 0 to 65,000. That doesn't mean you have a 16-bit camera. It might mean you have an 8-bit camera or a 12-bit camera that's outputting in 16 bits. And it's not an academic distinction. The camera really is limited by what its actual dynamic range is, as far as what kind of measurements it can make, the gradation of the signals you're going to see, and how fine, how well you're going to be able to distinguish bright to dark. So let's take a look at someone's camera. Everything is grayed out here. I've redacted this like an FBI agent to protect the innocent in this case. So this spec sheet lists whose CCD it is. In this case, it happens to be our CCD, but it's not our camera in this case. And the full well capacity is 100,000. And they list the read noise as 10 electrons. So the math is pretty easy. We take 100,000 electrons, divide it by 10, and we get 1,000 gray levels. However, you can look at the gain state on this camera, which is listed on this spec sheet here. The gain is 1.13 electrons, which when I do the math means that the camera is putting out on an 18-bit ADC. So you've got a camera that's actually 10 bits, right? Because 16 bits is 65,000 gray values. If we think about that, right? Go to 14 bits, it's half that, 32,000. 12 bits, it's half that at 12,000. You go half again. So really here we're at about a 10-bit camera at 1,000 gray levels, and it's outputting at 18-bit. So if you didn't know what I've told you here, you could look at this camera and say, oh, it's an 18-bit camera. It's putting out an 18-bit signal. But that actually has nothing to do with this camera's ability to distinguish light from dark, to encompass bright and dim things in the same scene, or to distinguish small measurements, small differences. You're just oversampling that same data in this case. And Bob the Tomato says, bruh, in this case, right? So why would someone do this? Why would someone build a camera that's kind of lying to you? Now you have the tools, right? So you can evaluate this for anyone. So part of my mission in life, I'm a scientist by training. I like to give people the tools to analyze things in your own and be able to, kind of tell what you're actually getting. And so that's part of the point of this. And why would someone build a camera this way? There's a few reasons. One is, sort of what I would call output inflation. If you're looking at getting a camera, the bigger number just tends to be better, right? If it's a quote 16-bit camera, what does that really mean? Now you can measure it. It doesn't just mean it has a 16-bit ADC, because anyone can put a 16-bit ADC on the camera. It's going to put out 16 bits. Could be that they get cheaper parts this way. If you're building a bunch of different cameras and have a bunch of different dynamic ranges, and you just put them all on a 16-bit ADC, you've only got to buy one part, right? So your parts cost for the ADC is lower. And it could be a lack of knowledge. Maybe, in some cases they don't know or don't care. I think that's more true outside the astronomy realm. The concept of dynamic range and this level of looking at things mathematically is not done in the consumer market, for example. So why wouldn't you just do this, right? Well, for one thing, your data is bigger. When you're saving data on a computer, if you're going to be doing something like lucky imaging, if you're going to be taking a lot of images that you're going to process and add later, a 16-bit image is going to take up more space than an 8-bit image, which is going to take up a lot more space or a lot less space than a 32-bit image. Each time you're doubling again. So, in an area of infinite hard drive space, maybe it's not quite as big a deal as it used to be, but you're still not really, getting everything you can. You're still wasting space. You actually get artifacts when you look at the data. You're going to see steps in the data where the camera is kind of filling in the gap, right? It's kind of interpolating data that's not there. And that creates these kind of oversampling artifacts, especially if you're trying to do something like spectroscopy or another type of experiment where the linearity and the sort of smooth gray values over time are going to make a difference. And you also wind up getting higher effective noise and slower readouts. The higher the bit depth of the camera, generally the noisier it is, the harder it is to read out. So, matching the ADC to the camera properly is going to give you a smaller data size, better data ultimately, and fewer artifacts and potentially faster readout. So I want to move on from full well and dynamic range. Hopefully that's clear to everybody, but if not, I'm happy to answer questions and move into a little bit of a more, one could say, new topic. Anybody who's looked at buying a TV in the last few years, or even a phone for that matter, will hear about high dynamic range modes or extended dynamic range modes. We tend to refer to this internally at Teledyne as extended depth of range to sort of prevent confusion with concepts like dynamic range, which are more fundamental. But you'll see this on a lot of cameras. And this is, we're actually building some cameras now that have off-board, sort of, I guess off-board meaning off-chip, but on camera still processing capability to do algorithmic computations in real time on the data. Other people are doing this too. This is what the TVs are doing. It's what the iPhones are doing. And I'm going to show you how it's done here. This is especially true for CMOS sensors. If you'll notice earlier in my example, the CMOS sensor, this has to do with how it's constructed. These devices tend to be thinner. Because it's thinner, it has a smaller full well. And we all know now that smaller full well equals lower dynamic range. So to compensate for that, they use this technique of extended dynamic range in order to kind of offset the smaller full well of the CMOS chips. You can also do this after the fact with a number of software packages too. So you can use this same technique after acquiring, say, a snapshot series of images. So exactly what is this technique? How does it work? So let's take a look at this image that I've got up here. This is an image taken with one of our cameras of a tritium source. So this is just a weakly radioactive source that glows in exactly the same way all the time. So it's like a reference light source. And it's brighter and it's dimmer. And as you'll see, we can count down to 4 dots pretty well here. By the time we get to the 5th dot, it's starting to fade out. 6 dots, pretty blurry. And the 7th dot is more like you're kind of imagining, that 7th dot. This first dot is very near the top of the scale on the camera. This is a 64-bit camera, so we're on a 65,000 gray value scale. And you can see that we're very near the top on this first dot. So it's almost saturated. That's about a perfect exposure. But the problem is even with this quote nearly perfect exposure, we're missing some of the data at the bottom here. So let's say you wanted to capture that. Well, let's do a longer exposure. So we do a longer exposure, and now we can get, dot 6, 7, and even a bit of dot 8 are all pretty good. And you can see that here in the data. The problem is the first two are now saturated. The first one and the second one are blown out. Not only is that ugly from an imaging perspective, if you look here, I'll show you the first one, nice, crisp, circle. Look at the second one here. The circle's kind of fuzzy, kind of blown out. In a lot of cameras, you'll see some streaking. We don't on this one. But not only that, but if you're trying to make a measurement on this or do anything scientific, the data is now invalid, because once you're saturated, you don't really know where the top of this number is. You don't know what the actual top is. So if you're trying to measure an intensity difference, this could be 10x higher, this could be 1,000x higher. You don't know. So how do we solve this? Well, what these extended dynamic range modes do is basically take two images like this. So the first one, the second one, bracket them, and then combine them on the camera. And if you do that, right, the extended dynamic range mode here, you can see you get everything in process. This first one is not saturated anymore. We're close, but we get one linear dynamic range image for the whole thing. So we're able to capture everything in one shot, basically. Even though to you, if the camera is doing this, it appears to be one shot. Behind the scenes, the camera is really taking multiple shots to do this. And it's interesting, on a CMOS camera, it's actually taking two samples of the same row and then combining them row by row. So it's even a little more complicated than this. But that's the basics of how it's done. Since you're all still here, I'll just give a brief little plug on Teledyne cameras. We do make these cameras available to the general public as well as to places like NASA. You'll find we're not going to be making the least expensive cameras you look at, but hopefully the best. And everything we make is built in the US. We generally have a lifetime vacuum warranty on all of our cameras. We've got software drivers for everything. And Woodland Hills are experts in incorporating these cameras into telescopes. We've been doing a lot of training with their application scientist, Peter, and we work a lot with other telescope companies like PlaneWave, et cetera, to make sure that integration is easy. So I list a few of our cameras on here. These are some of the CMOS cameras we make, as well as up to really big guys. If you're putting together like a professional class astronomy location, you can buy a camera that costs as much as a Ferrari if you want to. This is the latest one that will fit into that sort of entry. You can see next to the iPhone here, this particular chip, right? This chip alone is about the size of my head. So this is a really large array for doing sort of whole sky scanning at high speeds. And we just unveiled that at the latest SPIE astronomy show. So not too much of a plug. If you're interested in that kind of thing, feel free to reach out to Woodland. And, I'd be happy to help and advise as well. So that's everything I have presented for today. So without further ado, I'll go back up to this little kind of splash screen slide here and open it up for questions.
All right. So the best way to do this, guys, is if you type in your questions, I can read them out and we will do it in that particular fashion. Sorry, I'm just waiting for my cat there. So as you can see, she's wants to be a part of the show again. And then she'll step on my keyboard, of course. Come on, cat. So I got a question right off the bat when it comes down to the dynamic range, and it's essentially what it is that we're looking at. So I think a lot of people don't seem to understand what dynamic range is actually a measurement of. Do you want to go into it in a little bit more detail?
Yeah, I'm going to put this slide back up. There's kind of two aspects to it, and they're related, but not necessarily the same. So if I go back to this slide here, kind of showing the little gray bar, right? So the first way to think about dynamic range is it's the ability to distinguish between, say, 20 different shades of gray and 256 shades of gray. So if you want to make a measurement, like let's say you want to know two things are 1% different, right? Unless you can measure 100 shades of gray on the camera, you can't know if it's 1% different. In fact, you probably need to oversample. So you probably need more like 1,000 shades of gray to be confident that you can distinguish a 1% difference. If that makes sense. And then the flip side of this is because of this concept of full well capacity, because the bigger the full well, the bigger the dynamic range. A camera with a bigger dynamic range tends to have a much better ability to distinguish bright and dark in the same image. So, we've all seen a lot of images taken of, deep space objects where you've got a very dim part in one area and a very bright part in another area, say a star next to a cloud of gas or something like that. The ability to see both of those without one of them being saturated is also a function of dynamic range.
So out of interest then, when you guys are viewing this data, it's the camera itself can capture this dynamic range, these infinite shades of gray, but then there's another limitation that can happen is your actual monitor that you're using.
Well, and your eye. No, you're right on the money. So that's a really good point that I didn't discuss during this at all, and I kind of allude to it here. When I was taught this a long time ago, I was taught that humans can see 40 shades of gray. And then if you're like a radiologist, someone who looks at gray for a living, you might be able to do 100 shades of gray. Now, I guess the latest research says that that was actually a bit wrong. It's more than that. But regardless, it's a tiny fraction of what the camera can see. The camera, in a lot of cases, can distinguish 65,000, or with new 18-bit cameras, 130,000 shades of gray. Your eye can only see 40. So you make a good point, right? How can you relate that? The camera is seeing something that you can't see with your eye. And because of the way a computer monitor works, you can only display 256 shades of gray on a computer monitor typically, unless you have something really exotic and special. There are things that do more, but not that the average human ever interacts with normally. So what you do is the computer sort of helps you. What typically happens is the computer will scale the relevant area that you want to see of that portion of the spectrum down to 8 bits. And depending on what you're looking at, there's a lot of algorithms that can do that automatically, but very often people will tweak that manually. So there's kind of a fine art. If you're doing it for photographic purposes, you have the full dynamic range to play with on the computer, and the artist will take portions of that and bend the curve of the display, not just a straight linear curve fit, but do different types of curve fits to bring out the portions that you want from that, giant 65,000 bit range down to 8 bits that we can see, to make a nice looking picture. In the case of a measurement or a display, the computer will display sort of the relevant portion of the data for you to see. So it's a good point that the software you're using plays a large role in how you can visualize that actual data.
So yeah, questions are flooding in now. So let me just start with these questions, and we may end up circling back to some of these things, or the question gets asked in a slightly different way. But this is a good one right off the bat.
Yep.
Do sensor testing sites like DxOMark calculate dynamic range the correct way?
So I'm not familiar with DxOMark, so I will have to look into it. So I can look into that and get back to you. My guess is, I don't know. So is DxOMark calculating it off the camera?
I don't know off the top of my head. I've
Okay.
heard of this software before, but I've never actually used it.
Yes, I will. I'll look into it. And if you can take down the name of the person asking the question, I'll do my best to address it. But I can't do it at this time because I'm not familiar with that software. So
okay, yeah, we'll have to look that one up because I've heard of it, but I've just never used it. What are some generally available software applications that can implement EDR?
Yeah, so that's a good question. Practically every scriptable type of software on the planet has some EDR functionality. So, whether you're using, something like, I'm pretty sure that there's functionality is built in as an extension of Alpaca right now, if you're on the astronomy side. If you're in life sciences, Micromanager does this. If you have an iPhone and you put it in HDR mode, the iPhone does this. So virtually any type, and Photoshop does it as well. So virtually any type of imaging and software analysis package that you're going to be using has this capability. You might just have to look for it a little bit. The tricky part is it often goes by different names, but the name usually includes dynamic range or some permutation thereof. Usually if you see that in a post-processing function, it's doing a variation of what I described. And this kind of take two images and combine it is an oversimplification. There's better, more sophisticated ways to do it. And a lot of those are implemented in these software packages as well. And it's even an area, you know, like at the Advanced Imaging Conference, there were a few people that presented, I think, their own algorithms on how to do this, right? People are writing their own algos to improve on the state of the art.
Okay, next question. So does greater dynamic range help with the negative effects of light pollution?
I wish I could say yes. And I'm not a professional astronomer by trade, so I'm happy to be corrected on this. But in my experience with astronomy, the answer is no. Because once light pollution kind of corrupts the light you can gather, even higher dynamic range or trying to find ways to discriminate, as far as I know, isn't able to help with that.
That's interesting.
Now there may be ways for that to happen, right? But I don't know of, say, an algorithm to correct for light pollution that's dynamic range based. Doesn't mean someone hasn't done it or isn't working on it. It's just I don't know of that.
So just out of interest then, I mean, since that person brought this up, I think if I was looking at, say, image processing specifically with PixInsight, and I'm doing something like dynamic background extraction, to have more dynamic range, I'm able to pull out the bad parts of the skies essentially better than I would do with, say, an 8-bit image.
Yeah, no, that sounds right. That's right.
Yeah, so it can actually mean something then to that capacity.
That would be an interesting thing to test, right? That's something we could test empirically with taking a high dynamic range camera, low dynamic range camera on two different telescopes in the same scene at night, do what you're talking about and see what we actually catch, right? Because that would be it sounds like it should help in that scenario. But to my knowledge, no one's done a study or kind of proven it, you know?
Sounds like something for us to do.
Be a good thing to present. Yeah,
right.
That's a good experiment.
Follow-on question, does higher full well depth help with light pollution?
I would say possibly in the way that you just kind of outlined it, but what it'll let you do is take a longer exposure without saturating the camera. So you can potentially pull out something from amidst the soup more effectively, but you're not going to get like a binary improvement, I would expect. You might get a slight improvement, but you're not going to be able to, you know, go from this looks awful to this looks like amazing and there's no light pollution at all, right? You're probably going to get would be about a 5 to 10% improvement would be my bet.
Yeah, I think the biggest problem with some of this here is, if you can imagine, and this is wishful thinking, we can take a picture of something with light polluted skies. And if we can subtract the stars out and just leave just the light pollution, we could always subtract that out. But the problem here is we get all of that in one go.
Yes.
There's no way to block one versus the other. And even with a dynamic range as high as whatever it can become, I think at certain points, all we're doing is just increasing the amount of shading that we get between the two is the best way to describe it. So, I mean, from my perspective, at least anyway, I don't see how increasing any of these is really going to help with light pollution, because there's no way to subtract the bad stuff out from the way I'm thinking about it.
And the bigger problem I've seen that people are probably thinking about is, you know, if the light, depending on the level of light pollution you have, right? If the light pollution itself, if the signal you're getting from the light pollution eclipses the signal from the object you're trying to distinguish from it, then those photons all arrive intermixed at the detector, and the detector, you know, has no way of knowing which is which. It's just all a soup of photons that, you know, is eclipsing the object you want to see. And there's no magic bullet for that, unfortunately. I wish there was.
So let me ask you, this will be a nice question. How do you determine a camera based upon the dynamic range for a specific application? And you could use a few examples on that one.
Yeah, so I mean, the most common, I'll give one of the most common examples is someone who knows that they want to be able to distinguish between two objects of a certain intensity. And they say, you know, we need to be able to distinguish two objects that are 0.1% different, right? And in that scenario, you can back calculate the amount of dynamic range that you need in order to accomplish that objective. And there's a few different mathematical ways to look at what confidence level you need to get to make the measurement. But being able to distinguish between two objects with a small degree of difference is often one of the driving forces for, you know, getting a camera that has a certain dynamic range capability. That's kind of on the quantitative side. And that applies to, you know, if you're doing spectroscopy, you're going to get something that looks like this, right? A series of peaks. And whether or not you can get this little peak at the bottom here and this top peak is a function of the dynamic range. So, you know, very often if you're looking at different lines from different spectra, you want the dynamic range in order to be able to see the, say, really bright line and the dimmer line from, say, a certain star or from a certain gas nebula, from anything for that matter. That's kind of the geeky scientific way of defining it. On the flip side, you know, if there's a more qualitative, subjective way of looking at it, people who want to take interscene bright and dim objects in the same scene for photographic purposes that have nothing to do with measuring the difference, but just seeing the difference, where one isn't blown out and, you know, you've got the full range from a very bright object all the way down to a very dim object. Then you've got the data for both objects and you can scale the display to bring both of them out to make, you know, these kind of, again, gorgeous pictures where you've got bright and dim objects in the same scene. In some cases, you can do that by taking multiple pictures and recombining them. But often, let's say that you're trying to image something that's moving or not static, you know, and in those cases, it's always more convenient to do it in one shot. But if the object is moving, then you really need to do it in one shot because you don't have another way of doing it.
Okay, this is going to be a long one, so hopefully I might have to break this one down in several pieces, and we have plenty of time to do this, by the way. First of all, it says, sorry for the long question. Hold on. In an image captured using EDR, is it legitimate to compare the brightest pixel signal value directly to the diminished pixel signal value? That's part one.
Yeah, so it depends on the details of how the EDR is done. If it's a consumer type device or a consumer type software package, my guess is the answer is no. If it's a scientific software package or a scientific device, the answer is almost certainly yes. If it was me doing it, I would want to, there's a fairly really easy way to validate this. So one can actually get calibrated dynamic range sources. The thing I showed earlier from Kodak is one of these. So one can buy one of these little strips for a few bucks that has a series of gray shades like this. And what you know is that this one here at 2 is exactly 5 times less bright than this one here at 10 and 20, you know, 2x. You can actually image it, measure the values, and validate what the EDR is doing, just to be sure that you're right, because there's a number of ways to do it. So if it was me, I would want to validate it. This is kind of the simplest method of validating that. The method I show later using a tritium source on a black background is just as easy to validate with, but these tritium sources are not easy to come by. So whereas the plastic strip of gray values is very easy to come by.
I know he's just mentioned you've answered the full question, but I do want people to hear this because it's quite valid for the second part. It says, my impression to say of an iPhone HDR processing is a game is being played to merge the short exposure with the long exposure and no additional bits per pixels are created. Two input images are say 14 bits, and the final image is 14 bits. Does EDR example output more bits per pixel? Sorry, I had to ask that one as well.
Yes. No. And the answer is, if it's done right, the answer is yes. So the EDR can output more bits per pixel and gain actually more dynamic range than you go in with. That's kind of the point. So you'll see in my example here, the actual final image is now on 100,000 grayscale value scale, right? It goes from 16 bits to 18 bits of dynamic range. There's a lot more that could be said on this topic. So I had mentioned that, and I'll hit this since this guy seems to want a bit of a deep dive. We'll go a little deeper into the rabbit hole. The way that this is done on a CMOS cameras read out each row independently, and they can do a trick where they actually will often, the trick can be a little bit different. So don't hold me to the exact description, but you'll read out the same row two different ways. One has a sort of gain setup that's designed to measure the low part of the signal, and one measures the high part of the signal. Then the two are recombined, and you do this for every row across the whole thing. And so it was one of the first ways of building up an HDR image in real time on the CMOS sensor, which is pretty cool. And in a lot of those early cameras, I think it's largely solved now, but where that overlap between the two amplifiers occurs, you get kind of a flat spot in the data. So if you graph the gray value, you'd see this line going up, bit of a flat spot, and then another line. You know, it would look something like this if you can see my hand. And you know, that's obviously not good from a quantitative perspective. I think that's largely solved now. And what are people, you may see this term scientific CMOS camera. Scientific CMOS cameras are ones that do something like this and have corrected linearity across the entire full well.
It almost sounds like you just described Canon's dual pixel ISO thing. Sorry, there's a dog barking, I know.
No.
Yeah, it almost sounds like you've described Canon's dual pixel ISO thing that they've done. And in a lot of these other cameras, they have a bastardization of that particular wording. I mean, is this actually just something new, or is this another one of these lies that these cameras are telling?
Well, I honestly, the first time I know of this technique being used was actually with a Fairchild chip. And that would have been circa, boy, let me think back my brain a little bit here. This would be circa maybe 2007 on some of the first Fairchild sensors that were scientific CMOS. So that's the first time I know of it being used. And they didn't talk about it much because you had this flat spot in the data if you looked at it. So from their perspective, you know, it was something they were trying to not disclose was going on. Of course, people figured it out, you know, and then we're like, okay, what's going on with this flat spot in the data kind of thing, right? And then people realize you could start using this same thing to do more virtuous things like you're talking about here. So what you're describing could simply be, you know, lie might be a bit of a stretch, but it's certainly like a marketing slogan for this kind of a process being done on the camera, right? And I'll leave it to individual people if they want to describe all marketeers as liars or not. But, you know, given that I'm in marketing a little bit, I have to be a little more judicious.
So, I mean, how critical is the dynamic range on a camera for our purposes? I mean, I get it if you're looking at the James Webb, you know, you want to see everything, especially when it comes down to, say, infrared. But for our purposes, do we really need to be at 16-bit?
It depends on what you're looking at, right? So if you want to take, let's give a few different scenarios and examples. And it's a kind of thing where better is better.
Every day, an hour.
Oh,
sorry, I just muted him.
No worries. You know, it's the kind of thing where you could do something with, you know, thing A, right? But thing B is better and thing C is better than that. And in general, I think everyone wants to get the most for their money, right? Or their most out of their images. We spend a lot of time, right? Anyone who does astronomy knows how many nights do you have everything set up and then a cloud bank comes in and you're screwed for the night, right? I mean, this is like the life. So you want to get the most you can, at least I want to get the most I can out of the time that I have, where I actually have good observational conditions and can actually take nice images. And better dynamic range is going to get you better images in just about any scenario. So, the question you might ask yourself is, when do you need dynamic range? It's generally going to be if you're looking at something that's on the brighter end of the spectrum, because then you can take full advantage of the range of the camera. If what you're looking at is, let's say you're doing something where all you want to see is something that's really, really dim under the conditions with your telescope and your observations, and you've only got a few hundred photons that you're collecting with a 30-second exposure. Well, if you only collect 200 photons, your maximum dynamic range is 200 if you have a perfect camera, right? You're not going to be able to resolve more than one photon because that's a discrete quanta. And with some nice cameras and setups, you guys are getting down to taking images that only have a few hundred photons in them. And if that's the realm you're operating in, you don't have any dynamic range, right? You could buy the highest dynamic range camera in the world, and it's not going to help you. In that case, you need quantum efficiency, you need low noise. And dynamic range can actually work against you in that scenario. But if you're taking pictures of the moon, or you're making observations of the sun, or you want to be able to do spectroscopy on different objects and be able to see small peaks, in those scenarios, dynamic range is going to be king. It might even be more important than pixel resolution in a lot of cases. And so it's something you're looking at. If I was looking at getting a camera and I know I'm taking pictures of planetary observations and of the moon or stuff like that where it's very bright, I would look really seriously at the dynamic range of the camera. So it's, as with a lot of these things, right? It's astronomy. It's not for the, it's not the same as, I don't know, it's not the same as playing tic-tac-toe, right? There's a lot of variables. There's a lot of stuff to consider. And, dynamic range is often an overlooked one. So my goal today was to kind of give you the tools and a bit of a perception, right? If you're signal starved, you have no dynamic range. So a lot of this discussion is academic, but especially for brighter objects, higher dynamic range is going to let you really pull out the fine details and either get prettier pictures or better measurements.
I think you might have just started something with a lot of the people that do night sky imaging, because they're like going, oh, hold on a minute, I've just spent a lot of money on a camera that isn't going to give me anything.
Well, but, I mean, I don't know, right? I want to give you the tools so you don't make that. So you don't say that, right? That's my goal.
I mean, so the interesting part of it here is I do a lot of solar imaging specifically, and, I've got nothing but light, and here we are choking it down because I'm using, narrowband specific types that's measured in angstroms, which is even more crazy than a nanometer. Yeah. And that's the thing that this is where your cameras have probably come into play for somebody like myself. Even though I'm not doing the science behind it, the dynamic range is absolutely critical. And I've showed people the difference between shooting 8-bit versus 16-bit. Now, when I say 16-bit, I don't mean the camera's 16-bit. It's just the mode that it shoots in.
Yep. And presumably, right, one presumes, and that's one of the things I wanted to point out with today's talk, is presumably that 16-bit camera has higher dynamic range. Now you can calculate it, right? You can know, but it should be. In almost every case, it's really egregious to build a 16-bit camera that'd be lower dynamic range than an 8-bit camera, right? Like hopefully no one's doing that, but it's something to take into account. And it would be really interesting, you have access to a number of different cameras at Woodland, and you got your setup, and you could probably take some of the same images with cameras that have different dynamic range capabilities, true dynamic range capabilities, and see what difference it makes. It'll make a large difference, I guarantee it.
Oh yeah, no, it totally does. I've messed with so many different solar cameras, or cameras that we use for solar, should I say. And it's like each time I bring in another camera, it's like the step. To the average person, they may not see it, but to me, I see the difference like literally straight away. Especially because I've been looking at it for so long. I've been doing it since, I don't know, for the last 5+ years. And all I do is stare at monochrome data of the sun. So I've gotten to that point where I can just see a slight shift and go, what's going on here?
And most astronomers are in a different realm. Most astronomers are light starved. And for them, read noise matters more than dynamic range. But you're at kind of the opposite end of the spectrum,
yeah,
right?
totally.
With solar observations, right? So yeah, and so it's back to having the right tool for the you know the type of astronomy that you want to do.
So hopefully next month you're going to be back. Do you have any inkling on what you're going to be telling us or talking about?
I do. We actually have a set of topics for the series, and you know, you'd think that if I was smart, I would have been ready to answer that question. But give me a second, because I don't want to give you guys the wrong topic. We have a sort of order put together here, unless people decide they want to just kind of throw me off, in which case, you know, I won't be back. But
I doubt that somehow.
okay, good. Well, hopefully our people are you know, getting something out of this. And let me just look to the topics here. Sorry, bear with me just a minute. Yeah, so next up is actually going to be a really interesting one, and one that'll be exciting and take a little bit more background work for me. Is we're going to look at pixel size and the effect of pixel size on the resolution you get out of your telescope and your images, and how to know whether you've got the right pixel size match to the diameter of your refractor. So that'll probably be even a little more general. That'll probably be of general interest to everyone in a certain sense. And it'll be a good one to look at, because it relates both the camera and detector technology as well as the telescope technology, you know, because the point of the topic is one without the other doesn't make sense.
I think a lot of people are going to be really interested in that one, because it's always a common topic of pixel size versus telescope. Are you undersampled, oversampled? Yep. And it's one of these fantastic trigger conversations. And of course, everybody who is on this Zoom meeting, I do implore you to come back for this particular talk, because I will promise you it's going to be a really great argument. Have questions ready, because, you know, I love this topic. I really do. I love hearing about it. I love listening to the arguments about it. And I'm of the nature personally, and I know we're not doing this talk just yet, but me personally, I don't tend to care about pixel size and all that kind of stuff, because I'm in a position where I can say to somebody, just take the picture. That's what you want to do. Just see what it is that you're seeing first before deciding something's wrong. That's the critical part.
Yeah, no, and that's absolutely true, right? If you can't see what you're looking at, then the rest of it doesn't matter.
Yep. All right. Thank you very much, Mike. I love doing these talks, and I love listening to what you've got to say. I think all of us here genuinely have learned a heck of a lot about dynamic range. Hopefully, I don't suddenly see a load of cameras being tossed into the trash because of this talk when they realize that the camera isn't doing in what they want to do. So again, I appreciate your time.
Yep. Thanks, everyone, and see you next go round.